Solve the same circuit now using superposition this time. Now, superposition is not something that you would probably choose to use very often, but it does happen sometimes that it's very useful. And in fact, we are going to have one problem at the end of chapter 10 where it's actually required to use superposition, but we'll get there. So the idea is we're going to turn on one source at a time only, and I'll start by turning on the current source. So that means when I look at this here, I have my resistor, my inductor. I'm going to include the current source, 2 angle 0. I'm turning off the voltage source, and when we turn off a voltage source, it becomes 0, which is a short. And then I have a 1 here, and a 1 and a minus J. And so this right here gives us our circuit with the voltage source turned off. And it may not look like it at first, but if I want to find I0 here, this is actually a current divider circuit. So we can find I0 without doing too much work. And so what are we going to do here? We're going to say, okay, I0 is the total current source, and then it's going to be the impedance you're not at divided by the sum of the impedances. Well, we have to be careful because the impedance I'm not at is actually these two here in parallel. So I need to figure out now what is 1 plus J in parallel. What is 1 plus J in parallel with 1 minus J. And so to do that, you multiply them together, and then you add them. And this is a fun little thing here because what do we get when we do 1 plus J times 1 minus J? I'm going to get 2. And what do you get if you do 1 plus J plus 1 minus J? I'm going to get 2. So that means the impedance we're not at is 1 over the sum of the impedances. And this is going to work out to be exactly an I0 of 1 for our first source. Then we need to figure out what's going to happen with our second source, where we're going to have just the voltage source here. So I have my resistor, inductor. Remember what happens when you have a current source that gets turned off? It becomes an open. And we have this here. Now in this case, what I can do is, maybe the easiest way is to kind of take these two, all those together, combine them, then you'd have a series circuit which you can find the current, and once you find the total current, you could do a current divider over here. So I'll kind of do my work here. So the first thing I'm going to do is, if I combine those together, so 1 in parallel with 1 minus J is 1 times 1 minus J over 1 plus 1 minus J is going to be 1 minus J over 2 minus J. And then I can find the total current up here. I'll call that I. It's the voltage divided by the total impedance. So I'd have 1 minus J over 2 minus J, and then add on the 1 plus J from going around the loop here. And then once I find the total I, then my I naught is going to be that total I, 6 angle 0 over 1 minus J over 2 minus J plus 1 plus J times, again, now we're looking at just these two paths here, the impedance I'm not at over the sum of the impedances. And let's see here, 6 times 1 minus J is 6 minus J. This becomes 2 minus J, and we distribute that. It's going to kind of cancel out the first fraction, giving you 1 minus J. And then you're going to have 1 plus J times 2 minus J, And if you do a little bit of work there, that's going to be 3, let's see here, minus j plus 2 is plus j. So we're going to have 6 minus j over 4, which is 3 halves minus 1/4 j. Sorry, I actually made a mistake there. 6 times 1 minus j is 6 minus 6j. 6 over 4. So it's going to be 3 halves minus 3 halves j. Apologize for that. And so then by superposition, the final I0 is the sum of the two I0s we got. And we're going to get 5 halves minus 3 halves j, which is 2.92 angle negative 31.0. And so I0 of t is the same answer. Now in this one, it was kind of nice because I didn't have to worry about systems of equations at all. I could just combine some impedances and do, say, current divider or something like that and get the answer. So it's just kind of, your personal preference on what you think the best way to solve the problem is.